Hi and welcome to a lesson of multivariable calculus. So in today's class, we are going to talk about triple integrals. So in the previous lesson, we talked about the double integrals and their applications, that how can we use double integrals to compute areas bounded between the curves. So let us just recall that what does double integral mean. That, for instance, suppose that we have two curves. Let's say we have a curve that is a square root of x, and one of that curve is x squared. So the bounded area between these curves can be found using the double integral, that is accumulating all the uh, area by just dividing it into smaller regions, right? So this was the case for double integral, and now triple integral is the extension of this double integral. So you can think about computing volumes using the triple integrals. So here is a theorem that says that let G be a rectangular box defined by the inequalities that are these inequalities. If f is continuous on the region G, that is, if we have a region, for instance, we have some region G like this here, you can see there's some region bounding some volume. If we have a region of this kind, and we have a function f that is function of x, y, z, and it's continuous throughout the region, then this integral, uh, that is the integral of this function with respect to volume, that is dv over this region, is going to be equal to this integral over the individual limits in the x, y, z directions, and integral of this function dz dy dx, right? So this is also a type of the iterated integral, just like the double integral, right? Now let us compute some problems, and then we will get more clear understanding about the topic. So let us consider this problem. It's saying that let G be the wedge in the first octant. So let us just draw the XYZ coordinate axis. So this is XYZ coordinate axis. This is X, this is Y, this is Z. And the wedge in the first octant means all X, Y, Z are positive, just like you can think as in the case of XY plane, we have first quadrant as the where the XY are positive. So the octant that is cut from the cylindrical solid, y squared plus z squared less than equals to 1. So this solid looks like the surface we can just draw here. So it's in the x, okay, it's y squared plus z squared less than equals 1. It means that it is stretched in the x direction like this. It is stretched like this, right? So this is the cylinder, and we can just see that this is a cylinder stretched in x direction. And then we have the other curve, that is the plane y equals x. So y equal x, it looks like uh, this line that is in xy plane. And if I extend this, so it is going to be stretched in the z direction. So we can draw it like this. So this is the equation y equals to x. It looks like this in the xyz coordinate, right? And then we have the plane x equals 0, which means that this is the equation of zy plane. That is, we can just draw it in this manner. That is yz plane, so we can extend this like this, and then we have this plane like this. This is the equation for x equals 0, right? Now the volume that is bounded between all these curves is simply, we can see here that this curve here, this curve, and then we have uh, this curve here, and this will be a straight line since it's on the xy plane. So here we are going to have a straight line, and then this part, and then this part like this. So this is the region that we are interested in, and it is bounded by all these curves. So if I draw it separately here, so we can see that it looks like this. It looks like this. Sorry, let me draw it again. This is now this region, right? So here we have this region, and this is the region that contains some volume, right? So this equation, this surface is represented by the equation y plus z squared less than equals 1. And then we have y equals to x, that is the equation of this bottom plane. And then we have x equals 0, that is the equation uh, that only contains the xy plane, right? So now we need to find the volume of this curve. So now what we can do is we can find the limits of this region by simply finding the limits in the z direction first, and then in the y direction and x direction, or we can do it otherwise as well, first finding the limits in y direction, then x, and then z, and we can do it in all these ways, whatever we have the possible ways, right? Now what we can do here is that we just need to draw a straight line to find the limits in the z direction, and we can see that the topmost part of the region that is cutted by this line is this surface, that is y squared plus z squared less than equals 1. And then the bottommost surface is the xy plane where z equals 0, which means the inner limit, that is for the z direction, is going from 0 to this is z squared. So we can just find in terms of z. So it is square root of 1 minus y squared. So we are only considering the positive value of the z because it is in the first octant, right? So 1 minus y squared. Now, now we are left with xy limits. So now it is easier if we consider only the part that is in the xy plane, that is this triangular region. So now it looks like this, the line y equals x, that is this line. And then we have the line, this one here, that is y equals 1, right? So this is y equals 1. This is y equals x. Okay. And how do you know that this line is the line y equals to 1? Is that look at this curve, this one here. So this is the curve that is a part of the cylinder having this equation. So if we consider this point here, we have z equals 0, which means that y is going to be positive 1, right? So when z is equals to 0, so y square equals 1, which means y equals to positive negative 1, but we are only considering the first octant. So here we have y equals to 1. So this line here is y equals to 1, which is reflected here on xy plane. Right, so now this is the region for xy limits. So now we can find the limits in the x direction first, and then y direction, or y direction and then for x direction. So let us find it for the y direction first. So let us just draw a parallel line Let us do it in the x direction. So we draw a parallel line to x-axis. Here we have to see the topmost and bottommost part that is cutted by this line on this region. So the bottommost part is this one where x is equals to 0, and topmost part, rightmost part I should say, is x equals y. So the limit for x goes from 0 to y. Now the outermost limit is simply the limit on the y-axis, that is from 0 to 1. So it's from 0 to 1 here on y-axis. We can see that it's going from 0 to 1. So these are the limits for our region, and then we have the value z inside. So we have to now integrate this function, which we can do it easily, right? So the complex part of this problem is to find the limits of the region. Right now, let us talk about some other problem, and then we can see that how to find these limits. Now, see here, we have this problem. This one, find the volume of the solid enclosed between the paraboloids. Now, these are the paraboloids. So now we have to draw the paraboloids first. So let us draw it on the x, y, z coordinate system. So this is x, y, and z. Now the first one, paraboloid, having the center, having the vertex at the origin. So the vertex is at the origin, and it is cup up like this. So it looks like this. This is the paraboloid. And then the second one, that is 6 minus 7x squared minus y squared. So this is just shifted to 6 on the z-axis. So let us start it from here, for instance, like this. And its surface is elliptical, since we can see here that it is 6 minus 7x squared minus y squared. So this part shows that this is its surface is elliptical, and the surface of this paraboloid is circular, because here we can see that 5x squared plus 5y squared, right? Now we can see here that the region that is enclosed between these two paraboloid is this region, this one here. So it is enclosing some volume like this, if here you can see that. So this volume is enclosed by these two paraboloids, and we need to find this volume. Now what we can do is we can draw this region separately here. So this region looks like this one, and then we have this one like this. Okay, so it looked like somewhat spherical, right? So basically this is the volume bounded between these two curves. Okay, so now what we need to do is to find the limits, right? So to find the limit in the z direction, first we need to cut it with a line that is parallel to z-axis. So the topmost part and the bottommost part we need to consider for the limits. So the topmost part is the equation of this paraboloid, that is 6 minus 7x squared minus y, z equals, and this one is z equals 5x squared plus 5y squared. So now the limits are going to be from 5x squared to 5y squared to 6 minus 7x squared minus y squared. Now these are the limits for z-axis. Now since now we have to find the limits for x and y direction, therefore we need to consider only the xy plane. So the projection of this on the xy plane will look like where z is 0, therefore we can compare these two equations. Since z is 0, so we can write it in this way, that 6 minus 7x squared minus y squared equals 5x squared plus 5y squared, which in turn implies that 6 is equals 12x squared plus 6y squared. That implies that x squared, 2x squared plus y squared equals 1. And then we can write x squared over 1 over 2 plus y squared over 1 equal 1, which is the equation of ellipse. So using this equation, we can find the limits for x and y, right? So now we need to draw the ellipse here. Let us clear our drawings, or in fact, we should retain some of the stuff. So let us do it here. Now from here, we can find the limits for y, which will give us y squared equals 1 minus 2x squared, which gives y equals positive negative square root of 1 minus 2x squared. So the y limit is going from uh, negative 1 minus 2x squared to positive 1 minus 2x squared under the root. So we can write in this way. Now for the limits in x direction, we can simply say that if we have the ellipse like this, so the axis of this ellipse on this x-axis, it is 1/2 under root 1/2, right? Because this is a square. The standard equation of ellipse is centered at origin is this one. So this a squared equals 1 over 2, which means a equals 1 over square root of 2 plus minus. So the limits of x goes from negative 1 over root 2 to positive 1 over root 2. So this is how we can find the limits and then just integrate uh, by doing for integral in the z direction, then y direction, and then x direction. And we are going to get the volume bounded by this region. So we can just see here that how the solution goes on. So these limits we already have found. And then we have to simply first integrate with respect to z. Therefore, we will get z here with dy dx outside, and the limits from 5x squared plus 5y squared to 6 minus 7x squared minus y squared. And then solving this again and moving on in the similar manner, then integrating with respect to y and then with respect to x, we are going to get the result 3 pi over square root of 2. So you can just see the solution here by stopping the video at the moment, right? So this is how we compute the volumes of regions, right? Now let us consider the last example here. So we have this figure here. Now let us assume that we need to find the volume of this figure, and these equations are given here. So need to find the limits. First thing that we need to consider is to draw a parallel line that is parallel to z and check where it cuts at the top of the region and the bottom of the region. So the top of the region is this curve. So this is 1 minus x minus y. And the bottom of the region is xy plane, that is z is 0, so it is 0, right? Now to find the xy limits, just draw this triangle because we need to only consider xy axis now. So we have a triangle on xy axis like this. Right, this point is this is y, this is x. and this point is 1 comma 0, this is 0 comma 1. So the equation of this line can be found by using y equals mx plus c, where c is equals to 1 and m equals y2 minus y1, that is 1 minus 0, or x2 minus x1, there's negative 1, so it is negative x plus 1, that is 1 minus x. So the limit for y-axis is going to be from 0, because this is the region of consideration. So if we draw a parallel line, that is parallel to y-axis, sorry, this line, it is cutting this top part of the region and this bottom part. This top part is given by 1 minus x, and the bottom part is simply y equals 0, so it goes from 0 to 1 minus x. And on the x-axis, we can see that the limit goes from 0 to 1. So it is simply from 0 to 1, and we need to integrate with respect to z, y, and x to find the volume of this region, right? So this is how we can use the triple integrals in our daily life applications to find the volume bounded between the regions. So hope you guys understand this lesson. That's all for today, and in the next lesson we will be coming up with line integrals and some other stuff like Green's theorem as well. Thanks for watching the lesson.